So strange, so deeply weird, that even Albert Einstein called it spooky action at a distance.
Yeah, it's something that really shakes up our everyday intuition about, how things should work.
Exactly. And that phenomenon is quantum entanglement.
That's right. It's
hmm
fundamental to quantum mechanics. You have these particles becoming linked, interconnected. And distance just doesn't matter. It completely defies classical physics.
And it's not just some weird theory anymore, is it? It's having real impacts.
Oh, absolutely.
So today, we're going to really dig into this. How does this spooky action actually work? Where did it come from? And maybe most excitingly, what can we do with it? Stuff like computing, secure communication.
Yeah.
It's huge.
Right. So our mission today is to explore the theory behind it, look at some key experiments, really clever stuff, and then get into the applications that are, well, shaping the future of technology. We'll be looking at everything from the original papers right up to the latest breakthroughs.
Okay, so to really get why entanglement is so strange, maybe start with something familiar. Like if I cut an orange in half, hide the halves, and look at one.
Uh,
I instantly know the other half, right?
exactly. That's classical correlation. The state of each half, whether it has the stem part or not, was determined the moment you cut it. It was always going to be that way.
Simple enough.
But quantum entanglement is different. Take two photons, maybe created together, and they become entangled. If you measure a property of one, say its polarization, you instantly know the polarization of the other one, instantly, even if it's miles away.
Okay, so far it sounds a bit like the orange.
But here's the crucial difference. With the orange, the property was always there. With entangled particles, before you measure them, they don't have a definite state for that property. They exist in a kind of fuzzy state, a superposition of possibilities.
A superposition,
Yeah.
like both states at once.
Sort of, yeah. It's only when you measure one particle that its wave function, the mathematical description of its quantum state, it collapses. It settles into one definite state. And the spooky part is, this collapse instantly forces the other particle into the corresponding state, no matter the distance.
Right, that instant connection across space. So that's the spooky part Einstein was talking about. Podolsky and Rosen wrote that famous EPR paper in 1935, didn't they? Questioning if quantum mechanics was even complete.
Precisely. They argued this instantaneous effect seemed impossible without some, hidden information traveling faster than light, which relativity forbids. Or maybe the theory was just missing something. That's what led Einstein to call it spukhafte Fernwirkung, spooky action at a distance.
It's funny, though, Einstein called it spooky action, but wasn't Schrödinger who actually gave it the name entanglement?
Yes, exactly. Erwin Schrödinger read the EPR paper, and in his response, he coined the term Verschränkung, which translates to entanglement. He saw it wasn't just a weird edge case. He said it was the characteristic trait of quantum mechanics, the one that forces its departure from classical lines of thought.
So it's not a bug, it's a feature. A really, really weird feature.
A primary feature, yeah. Nothing like it in classical mechanics.
Okay, quick clarification, though, because instantaneous action sounds like faster-than-light communication. But it can't be used for that, right? You can't send a message using entanglement.
That's a critical point. No, you absolutely cannot. While the correlation is instant, you can't control which state the first particle collapses into. It's random. So you can't force it into a state to send a specific bit of information to the other side faster than light. You only know the correlation after you compare measurements, which requires classical communication.
Got it. So no FTL messages.
Yeah.
But how did scientists become so sure these correlations weren't just, like the orange? Maybe there were hidden instructions inside the particles all along.
That's where the physicist John Bell comes in the 1960s. He devised a mathematical test now called Bell's inequality. Basically, it sets a limit on how strong correlations could be if they were based on predetermined local properties, what we call local hidden variables.
Okay.
And then experiments were designed to test this. And what they found, consistently, is that the correlations between entangled particles are stronger than Bell's inequality allows for classical explanations. They violate the inequality.
So the results exceed what classical physics says is possible.
Exactly. These experiments provide really compelling evidence against local hidden variables and strongly support the standard quantum mechanical description of entanglement. The spookiness is real, it seems.
Okay, so the theory dates back. Bell's theorem points the way. But when did someone actually, see this in a lab for the first time?
Well, one of the earliest and really pivotal experiments observing entanglement with visible light was done by Carl Kocher, right here at UC Berkeley around the mid-1960s. He was directly inspired by the EPR paradox and wanted to find the simplest possible system to test these quantum predictions.
Simple, huh? I bet it wasn't that simple to build.
No, definitely not simple in practice. Kocher's idea was clever, though. He used calcium atoms. When you excite them just right, they emit two photons in a cascade, one green, one violet. The key prediction from quantum mechanics was that these two photons should be entangled in their polarization.
So he needed to catch both photons from the same atom.
Exactly. He needed two detectors and electronics that could register coincidences detecting a green photon in one detector and a violet photon in the other at almost exactly the same time. Then he'd put polarizers in front of the detectors and see how the coincidence rate changed as he rotated the polarizers.
Sounds tricky. What were the big challenges?
Oh, plenty. First, he needed a strong UV light source to excite the calcium atoms efficiently. Commercial ones weren't good enough, so get this, he built his own 500-watt hydrogen arc lamp.
Wow. Okay.
And then the signal itself was incredibly weak. His calculations predicted maybe only one coincidence per second, even without polarizers. He wrote that getting the data would need considerable care, patience, a long observation time, and some courage. You gotta admire the dedication.
Definitely. Did it work right away?
Not quite. There was a classic lab moment, a real aha. After weeks of getting frustratingly low signal, almost nothing, he figured out the problem. He was cooling his photomultiplier tubes to reduce noise, right?
I guess.
But the cooling also affected his narrowband interference filters, the things isolating the specific green and violet colors. They were thermally sensitive, and the cooling had shifted them off resonance, so they weren't letting the right photons through.
Oh no. So close.
Right. So he added a small heating coil to the violet filter mount, warmed it up slightly, and bam. Within an hour, in December 1966, he said he got a clear, unequivocal coincidence signal. Imagine the relief.
I can only imagine. So what did the results show about entanglement?
This is the beautiful part. When he aligned the polarizers for both photons parallel to each other, he detected coincidences, just as you'd expect. But, and this is the key, when he set the polarizer axes perpendicular to each other, the coincidence rate dropped to zero, nothing.
Zero. Not just low, but zero.
Zero. Within the experimental uncertainty, this perfect anti-correlation when perpendicular and strong correlation when parallel was exactly what quantum mechanics predicted for entangled photons. It was, as he put it, a signature of entanglement that has no classical analog.
So not like the orange halves at all.
Not at all. And this wasn't just microscopic. His detectors were 40 centimeters apart. It was a macroscopic demonstration of this quantum link. Kocher's results were later confirmed and refined by others, like Friedman and Clauser, setting the stage for the even more rigorous Bell test that eventually won Aspect, Clauser, and Zeilinger the Nobel Prize in 2022.
Incredible. So that really cemented entanglement as a real physical phenomenon, not just theory.
Absolutely. It moved from paradox to proven reality.
Okay, so it's real, it's weird, we've proved it. Now, the big question, what can we actually do with this? You mentioned it's like a resource, a quantum superpower.
That's a great way to put it. Entanglement allows us to perform tasks in information processing and communication that are just impossible classically. It's a key ingredient in many quantum technologies.
Like quantum computing.
Exactly. Quantum computers harness entanglement, along with superposition, to tackle certain problems exponentially faster than any classical computer ever could. Think Shor's algorithm for breaking common encryption or Grover's algorithm for searching databases much faster.
And entanglement helps keep the quantum computation stable, right? Something about error correction.
Yes, that's crucial. Qubits are incredibly fragile, sensitive to noise, what we call decoherence. Quantum error correction, or QEC, uses entanglement cleverly. It spreads the quantum information across multiple physical qubits in an entangled state, so if one gets disturbed, you can still recover the original information. It's essential for building fault-tolerant quantum computers.
Okay, computing is one big area. What about communication? You mentioned security.
Right. Quantum communication, especially quantum key distribution, or QKD. The thing is, the encryption methods we rely on today, like RSA, are based on mathematical problems that are hard for classical computers.
But easy for future quantum computers, potentially.
Precisely. Shor's algorithm could break RSA. So we need something new, something quantum-proof. QKD offers security based on the laws of physics themselves. If you use entangled particles to generate a secret key between two parties.
Like Alice and Bob, the classic example.
Alice and Bob, exactly. If an eavesdropper, let's call her Eve, tries to intercept and measure the entangled photons to learn the key.
She inevitably disturbs the quantum state, right? Because of that measurement collapse we talked about.
Exactly. Her eavesdropping introduces detectable errors, changes in the correlations that Alice and Bob expect to see. They can test for this, and if they detect anomalies, they know someone's listening, and they just discard the key and start over. It's fundamentally secure.
And there are different ways to do QKD. You mentioned protocols like BB84, E91.
Yeah, there are a few main types. BB84 is probably the most widely implemented. It doesn't strictly require entanglement, but uses single photons and different measurement bases.
Yeah.
It's quite practical, high key rates, but maybe has some theoretical vulnerabilities. E91, developed by Arthur Eckert, is based directly on entanglement and Bell's theorem. Its security is arguably stronger, tied to the non-local correlations, but it's technically harder to implement, so key rates are often lower.
And decoy state.
Ugh. Decoy state QKD is a clever enhancement, often used with protocols like BB84. It helps defend against specific attacks, particularly the photon number splitting attack, by randomly sending pulses with different average photon numbers, some strong, some weak decoy states. It helps balance security and practical performance.
Okay, so computing, secure keys. What else can this quantum superpower do? Sensing.
Yes. Quantum sensing is another huge area. Entanglement can boost the sensitivity of measurements beyond what possible classically, beyond the so-called standard quantum limit.
How does that work?
Well, by entangling multiple probes like atoms or photons, you can make them act collectively. Their measurement outcomes become correlated in a way that enhances the signal relative to the noise. For instance, improving high-resolution NMR spectroscopy for looking at molecules, creating incredibly sensitive magnetic field sensors, designing better atomic clocks or inertial sensors, things you need for navigation. There's even research into covert sensing, where you use entanglement to probe something while hiding the probe signal itself in background noise.
Hiding the probe. That's sneaky. And what about imaging? Can you take pictures with entanglement?
Sort of, yeah. There's a technique sometimes called ghost imaging or interaction-free measurement using entanglement. You can essentially get information about an object, even form an image, using photons that never actually interacted with the object.
Wait, how?
You use pairs of entangled photons. One photon from the pair is sent towards the object, while the other is sent directly to a camera. By measuring correlations between the photons that did potentially interact with the object, even if they were absorbed or blocked, and the ones that went straight to the camera, you can reconstruct an image. It's another one of those mind-bending quantum effects.
That truly sounds like science fiction.
Yeah.
And is entanglement still just for photons and atoms, or are we seeing it elsewhere? You mentioned quantum gravity.
Right. On the more theoretical frontier, entanglement is popping up in discussions about quantum gravity. Some ideas suggest that maybe our perception of time passing, of the universe evolving, is actually related to entanglement growing between different parts of the universe, or between a system and a clock. There are even theories, like the it from Quebit idea, suggesting that space-time itself might emerge from the entanglement patterns of underlying quantum degrees of freedom.
Space-time emerging from entanglement. Okay, my brain hurts now.
Yeah, it gets deep. But it's not just theory. Experimentally, entanglement is being confirmed in more and more systems. We've seen it confirmed between top quarks fundamental particles at the LHC just last year.
Top quarks? Seriously?
Yep. And even in macroscopic objects, tiny vibrating drum heads, mechanical oscillators researchers have managed to entangle them in the last few years. And very recently, hints of entanglement effects even inside protons, between the quarks and gluons holding them together. So it seems to be everywhere, from the smallest scales to potentially the largest.
That's incredible. It really is fundamental. So if we can create and control entanglement, the ultimate application seems like building a quantum internet, right?
Yeah.
Using these secure connections globally.
That's the grand vision, yes.
Yeah.
A network where nodes are connected by quantum channels, sharing entangled particles for ultra-secure communication, linking quantum computers, enabling advanced sensor networks.
Is that still just a vision, or are we actually building pieces of it?
We're making real, tangible progress. Just this year, February 2025, there was a significant breakthrough. Researchers from Oak Ridge National Lab, EPB, the municipal utility in Chattanooga, believe it or not, and the University of Tennessee at Chattanooga.
Okay.
They successfully transmitted an entangled quantum signal over a standard commercial fiber optic network. And the amazing part, they kept it running continuously for over 30 hours without interruption.
30 hours. Continue on regular fiber. That sounds huge.
Yeah.
How do they manage that? Quantum signals are usually so fragile.
It was a major step for practicality. The key was using a sophisticated system called automatic polarization compensation, or APC. Polarization is how the photons were entangled, but polarization gets scrambled easily as light travels through fiber optic cables due to temperature changes, vibrations,
Right,
stress.
the signal degrades.
Exactly.
Yeah.
This APC system uses a separate classical laser signal sent alongside the quantum signal as a reference. It constantly monitors the polarization changes on this reference signal using a very sensitive technique called heterodyne detection, and then actively adjusts optical components in real time to undo those changes for the quantum photons.
So it actively corrects the errors as they happen.
Precisely. And it worked well enough to maintain the entangled link with effectively 100% uptime for over a day. The significance, as the researchers pointed out, is that the people at either end of this transmission won't notice any interruption and don't need to coordinate scheduled downtime. It makes quantum links much more like the reliable internet connections we're used to.
That really does bridge the gap towards practicality. But I assume there are still big hurdles to overcome before we have a global quantum internet.
Oh, absolutely. Significant challenges remain. The first is still photon loss and signal degradation over long distances. Fiber optics absorb and scatter light. The solution there involved developing things like quantum repeaters, which can take a weakened, entangled state, purify it, and effectively extend the range using a technique called entanglement swapping.
Quantum repeaters.
Yeah.
Okay.
What else? Decoherence is always a big one. That's the loss of the delicate quantum state due to interaction with the environment noise. For computation, we need fault-tolerant designs and error correction. For communication, we need better shielding, maybe operating at very low temperatures, and robust protocols.
And cost. This sounds expensive.
High implementation costs are definitely a factor. The specialized lasers, single photon detectors, cryogenic equipment, it's not cheap. But there's huge progress in miniaturization, integrating quantum components onto silicon photonic chips, much like we did with classical electronics. That should bring costs down eventually.
Like Moore's law for quantum.
Maybe something like that, yeah. And finally, there's the need for standardization. Right now, different research groups use different protocols, different hardware. For a global network, everyone needs to agree on standards, like how TCP/IP works for the classical internet. Organizations like the ITU and NIST are working hard on this.
So, progress on multiple fronts, but still work to do. Are countries actually investing in building these networks now?
Yes, absolutely. China launched the MISHIS satellite years ago for satellite-based QKD experiments, demonstrating entanglement distribution over thousands of kilometers. Europe has the EuroQCI initiative, aiming to build a secure quantum communication infrastructure across the EU. The US also has various government and private initiatives. The race is definitely on.
It really feels like we're at a tipping point.
It does. The foundations are being laid.
So, just to wrap up, we've journeyed from this deep philosophical puzzle, Einstein's spooky action, through some really ingenious, difficult early experiments.
Yeah, like Kuchar wrestling with his filters.
Right, to now where entanglement is this core resource, the engine behind a whole new wave of technology.
Exactly. What started as maybe the weirdest, most counterintuitive prediction of quantum mechanics is now proving to be the key to unlocking breakthroughs in computing, in secure communication, in sensing capabilities that classical physics just doesn't offer. The spookiness turned out to be a superpower.
It's truly remarkable. So, a final thought for you, our listener. As we keep pulling back the curtain on entanglement, as these quantum networks start to connect cities, maybe even continents, what things that seem completely impossible today might become routine in your lifetime? Think about it. How might harnessing this fundamental interconnectedness of the universe change the way we live, work, and understand reality itself?